Epoxidation of alkenes. Here's an alkene, here's the peroxy acid. The result is an epoxide and an acid. So let's have a look at how this happens. So we've got an alkene, and in this reaction, a lot of different things are happening at once. So we're going to have a look at what's going on first, and then we'll have a look at why that is happening. So here we've got electrons traveling all over the place. The end result really is this bond here between these oxygens and this oxygen hydrogen. These bonds are going to be transferred to these carbons. And at the same time, new bonds are going to form between this oxygen and hydrogen, this oxygen and carbon as well. So let's have a look at the transition stage now, so get a better understanding of what's going on. So the dotted green lines are the old bonds, the dotted red lines are the new bonds forming. This reaction is not one thing happening, therefore the reaction takes place. This happens, therefore this. It's a lot of competing factors that cause the reaction to take place. And this will help us gain an understanding of why this oxygen is the one that reacts and not this one right here. Because if we think about it from an electron perspective, it would seem to make sense that this oxygen is more reactive because it's competing with an oxygen and a carbon, where this one is competing with an oxygen and a hydrogen. So this one should have slightly more electron density about itself. Why does this oxygen not react instead of this oxygen? It seems like this oxygen would be a better candidate for attracting electrons to itself. Besides the possible problem where this carbon group might be very large and bulky and cause steric interference, but if that was not a problem, we have to understand how the total reaction works. This is a reaction where it's a lot of slight attractions going on, weakening bonds slightly. So as we can see here, this oxygen is slightly attracted to this hydrogen, and when there's this slight attraction, it's going to weaken this bond right here slightly and this bond over here slightly. As this bond weakens right here, then this oxygen, which is slightly more positive and competitive for electrons, as it's in a state where it's more electronegative than carbon, so it's going to be able to pull slightly more on the electrons that are weakening from this bond to itself. And as a result of this bond being slightly weakened and this bond being slightly weakened, now that gives an opportunity for the oxygen on this right here to attract the pi electrons of the double bond. So that's the whole reason that this reaction is allowed to take place. So if we go back and have a look at this oxygen, if this oxygen were to be the one reacting over here, there is no alternative bonds where this oxygen right here can easily replace it with something else, and this carbon can replace it with its bond with something else. It's far away. So this reaction works because these things are nearby each other, and they can quickly, as those bonds are weakening slightly, fill it in with something else, something that can take its place. Where this oxygen, there's not that opportunity for the other atoms nearby it. And the ultimate result is this epoxide. So hopefully this was helpful in understanding at the dynamic of the finer points of this reaction from an electron perspective.